Well, good afternoon, everybody. Hopefully I won't bore you too bad with the presentation or after lunch. As he said, I am a engineering group leader in generation engineering. So in our company, we have 5 generating plants, and we are the internal mechanical engineering consulting group of that. So a little bit about the company: around 8,000 megawatts of capacity. We have roughly 1.3 million customers, and we are around 2/3 of the state of Kentucky that we provide power to. And then we have little pieces of Virginia and Tennessee, where it's in the mountains, and the only reason that we provide them power was because it was cheaper to run the lines from our system than it was to run them from the systems in Virginia or Tennessee. So we have a few customers there. And then also we are a gas company in the Louisville area, and we have around 300,000 customers that we supply gas to. So what is in our service territory? So if you're familiar with horse racing, the Kentucky Derby is held in Louisville, Kentucky every year. It'll be coming up in the next couple weeks. Actually, it's the first week of May. There we go. So Churchill Downs in Louisville. Don't know if you ever realized how much a horse costs, but this horse sold at auction for $1.5 million. And anytime I'm going to one of our plants, it's near Lexington, Kentucky, I drive by miles and miles and miles of this fence. And I hate to know how much money they pay to just paint that fence white. And some of it is painted green and some of it is painted black, but it all looks pristine every time I drive by it. So somebody is spending a lot of time painting fence. Another thing is the Louisville Slugger, largest bat supplier in the world, right in downtown Louisville. It's about 5 blocks away from where my office is. It's home to the largest bat in the world. It's 120 feet tall and weighs 68,000 pounds. And for scale, you can see the little boy standing next to the bat. And finally, probably what we're most well known for is bourbon. Parker Beam, who was the master distiller for Heaven Hill, once said that you can make bourbon anywhere, but to sell it, it has to be made in Kentucky. So a lot of these are some of my favorites that I drink. I have a hobby. I put on whiskey tastings for the local non-charity or for local nonprofits that I do a couple times a year. So I actually make it up to Chicago almost every year. I didn't make it this year for Whiskey Fest. It's one of the largest whiskey events that you can come to if you really like trying lots of different whiskey. It's the place to be. It's like 3 hours, and there's like 500 different types of bourbon that you can try and scotch. So why do we care about condition monitoring? So I think yesterday we saw a curve similar to this. It's called the PF curve. So it's to find the point of a problem detection here to the point of failure over here. So what we want to do is always find this point of problem detection. We want it as far back on this plot as we can get it. So because we have scheduled outages, typically they're once a year. Sometimes they're once every 18 months. So we try to find these problems as early on so that we can plan for that outage, so that we don't have it happen like here. If we detect it over here, it's too late, and it's going to fail before an outage occurs. So traditional monitoring. This does not look right, but okay, we'll go with it. Traditional monitoring, we have some points that are monitored, and there's an alarm limit that operations monitors. As vibration increases or whatever increases, until it hits an alarm point, nobody knows, nobody cares. So then finally, the vibration will go up above an alarm point. So then all of a sudden, alarms start going off in the control room, and then people start getting calls. So as a corporate predictive maintenance engineer and a level 4 vibration analyst, generally speaking, on large equipment, when they went into alarm, somebody in our group would get called. So the next thing I would do is I'd get in my car and go to the plant. So for us, from the time I would get a call to the time I'd get out to the plant could be anywhere up to 3.5, 4 hours, depending on the plant we were going to. So in the meantime, the plant's waiting, not really knowing what to do, or they're trying to make a best educated guess that they can as to what to do. So we get to the plant, or I get to the plant, and I usually go into some little room that is a electrical panel room, and sit down at a desk with one PC screen, trying to start collecting data to try to make some kind of decision on what is going on with the machine. So if anybody is familiar with this software, you know that it is not the easiest software to gain good data out of, or not very quick to gain insightful data from. So just trying to collect the right data to be able to analyze the problem can take 1 to 2 hours. And for me, the only time I ever use this software is when there's an issue. So half the time I'll go down there and it takes me 30 minutes to remember how to use the software because I don't use it often enough. And the other issue with this is all this software and the data is proprietary. So there is no getting the data out of that room. The only way I can get the data out of that room is to take a screenshot of what I'm looking at, or to print off basically a PDF of a screenshot. And that is the source of the data. So if I want to pack up the data and send it to somebody else, or if I want somebody else to be able to see it while I'm looking at it, there's not a real good way to do it. So what we wanted to do was liberate the data. We wanted to get all this meaningful information that we have on this server that is locked up in a room out so that other people could look at the data and make decisions quicker. Whoops. So we had some requirements when we looked into this. The first one was it had to have remote accessibility. So we wanted anybody that we gave the rights to be able to access the data. 2, for us, it had to be SIP compliant. So anybody in the power or anything that has to do with critical infrastructure, SIP is critical infrastructure protection. So since we're a power utility, people like to hack into us, and these systems that are here, they protect the turbine. So if somebody goes into one of those systems and makes the trip level 0 mils, it's going to immediately trip the turbine. So our compliance group is always very, very leery of anybody doing anything that touches this equipment because there is the SIP compliance issue. We wanted the ability to store the data in Historian. We use Pi, so Historian is just basically a big data logger. All the data goes in as a repository, and it can be accessed by anybody in the company with the right access to it. We wanted a better user interface, so something easier to use than our existing software, and something it didn't take 3 or 4 days of training to learn how to use it. So something that we could do a 4-hour training and somebody would be at least efficient at using the software. Oops. Customizable parameters. So the data that we did get out of the old system into Pi was only the overall value of vibration. So we wanted to be able to customize what data came out of it. So we wanted overall, we wanted 1x peak and phase, we wanted 2x peak and phase, we wanted gap voltages. We wanted more data that just wasn't available to us through the old system. And then finally, we had a preference for a thin client. So thin client, thick client. A thick client, if you have Microsoft Office installed on your computer, that is a thick client. If you're using Office 365, or it's off the it's web-based, then that's thin client. So the advantages of thin client working with IT is that anytime there's an update, we just update the server. And once the server is updated, anybody that's going to that website, it's already updated. So there isn't this whole process of trying to go through to make sure everybody's on the same revision. You know, if somebody may not have their computer on the network the night when the update was gone, so it didn't get pushed to them. So then the next day, everybody's like, well, we don't have access to the data anymore. So by going with a thin client, that eliminates those issues, and it makes managing the software easier from an IT perspective, which getting IT buy-in is a huge part of this whole process. So it came down, we had two options. We could either use the system that we already had, and they had a way that we could replicate the data. So it basically would be setting up another server that's outside the control system firewall and send data through a data diode one way out to that system, and then it would be accessible from others in the company. So that has pros and cons to it. The pros, any of the data that was in that system and anything that we were monitoring would automatically be moved into the replicate, so we'd have access to it immediately. The cons to it was we were keeping the same software that we had issues with, and we still had potential future SIP issues. These SIP standards change almost every year, and so there was a worry that we would do this, spend a bunch of money, and the SIP standard would change, and it would basically make everything we did obsolete and not work anymore. And the second option was to install new hardware and software. So basically, to piggyback off of the hardware that we already had that was tied into the sensors, piggyback a new hardware that would read that sensor data and then send it to a new software. The other pros to that was it would be one software for the entire fleet. So not all the plants use the same protection hardware and software. So at different plants, we had different protection devices. So by integrating this, a new system, it would be one hardware and software across the whole fleet. So we received 3 quotes for that hardware software system, and we chose basically the only one that met all of our requirements. It's not up here, but it was National Instruments and Insight CM. They did a development through EPRI and Duke, and they already had the hardware, so they had to develop the software to mate into it. So over here, just a brief architecture. This is the protection rack here, and then we installed these compact RIOs inside the panel with it, and the protection rack has buffered outputs on the back of the panel. So those buffered outputs, we could tie right into the new hardware, and there's no issue with SIP compliance. So that goes into the hardware. It recalculates all the data, and the hardware is pretty robust as far as what kind of inputs it can take. So you can have key phasers, accelerometers, prox probes, bolometers, temperature, current, flux, and many, many more things. So it's pretty much sensor agnostic. They don't care what sensor data goes into it. So it reprocesses all the data, sends it across our business network. So we've gone away from the control network. So we have gotten away from the SIP requirements because we're not on the control network. And then it goes to a local server that calculates more features and things on it. And then from there, it goes into the Pi historian. So this is a balance of plant installation. So in balance of plant installations, we didn't have protection already. So we actually installed the compact RIOs out next to the machine and ran wiring to accelerometers out on the bearings. And the big thing was, so all this data that we're streaming that is all based on alarm values, change in engineering unit, or time, and it's all configurable to however we want it, all goes to our MND Center, our Monitoring and Diagnostics Center. So the next question, how many of you are familiar with a Monitoring and Diagnostics Center? Nobody. Well, here it is. Does everybody know what this is? It's a still from Kentucky. So this is the way I kind of picture a Monitoring and Diagnostics Center. So the MND Center takes thousands of measurement points. So all this feature data that we're sending now into Pi, it takes all that data, somebody creates a model. So inside of Pi, all of the machines are set up so there are templates. So each machine template will have, temperature points, pressure points, vibration points, and it's all set up as a template. So then you put it in this model, and the model will take all those templates and it will predict the value that it should see of a data point. So once it predicts that value, it starts screening for changes. And if it reaches a threshold, it'll alert for diagnosis. So then a person will actually look at the data to say, is this an issue or is it not an issue? So if it's an issue, then it gets escalated to the plant, and then we end up with one or two actionable items. So all this continuous data is being fed into this system, and then out of all this data comes one or two actionable items. So how does it work from a more technical standpoint? So this is what the MND trend would look like in the MND Center. You got the red line is a predicted value, the blue line is the actual value, and then this green area is an upper and lower bound of the actual value. So we'll put in a year's worth of data. And inside that year, you got temperature changes, load changes, lots of different system changes. And so where you'd have a typical alarm system, you have to set your alarm level above all those environmental changes, because if you didn't, every time the temperature would drop, you might go into an alarm. So by going into an MND Center, it learns what that alarm level should be at all these different conditions. So as you can see on this point here, this blue trend line here, over on the right-hand side, it starts going beyond this bound. And every time it goes beyond this bound, you get these little highlighted stripes. So by the time here, it's completely beyond the bound. So the MND Center would get an alert, and they would diagnose what is causing that to go beyond its upper bound. And then if there's a reason for it, then it would get escalated to the plant as an issue. So with remote monitoring implemented, now a value starts to increase, and the MND Center will see it. So we're below an alarm point, but now we're getting alerts earlier. And we're also getting alerts on things before that we wouldn't have gotten an alert on. We've gotten alerts where we've had catches on white bearings. That was something that was always a hard thing, but now that we have DC gap voltages going in to the system, it actually looks at the distance the shaft is away from the tip of the prox probe. So the MND Center can see that change and see the drop and actually alert on a potential bearing wipe. We've had issues where a bearing was actually not lubricated, and the MND Center picked it up before we had actually seen it in the vibration, because it was just a kind of a blip that just continued to increase, and it was above what was normal, and so they alerted on that. So when we get the alerts, now, rather than me having to go to a plant and look at the data, I can just sit at my desk, or whoever gets the alert can sit at their desk, and they can look at this data. And before, where everything was like just one window for one type of plot, now everything is tied together, and everything is interconnected in these plots. So if I click anywhere up on this trend, on any of these trends, it'll give me that waveform and spectrum, an orbit, a Bode plot for this whole time range. And the other good thing is, before, where all I had was whatever the rack was seeing for data collection, now I can actually pull Pi points back into the system. So where it used to just be just the vibration data was all I would see trends on, I can actually go in and say, well, I want to see the load. I want to see what the megavars were on the generator at the time all this was going on. What was the bearing temperatures on this system? And I can pull all that in and plot it right here in the trends, and then go through and be able to do more analysis right here, and then when I want to see the detailed vibration data, go in and look at it at any given point. So for some reason, the slide was not supposed to look like this, but it was supposed to be that the vibration went up, we caught it with the MND Center, then we went into a planned outage. Oh, there we go. There's the planned outage. And then we came back online, and everything went back to the way it was prior to the notification. So where are we now with this system? You can probably figure out where, whoops, that didn't work. Well, anyway, tag on. So now we've been able to take the dot that we had down here, that would be a bad thing to have it way down here, and we've been able to push it further up this curve in order to find problems sooner. Which, with planning, we're using Visual Sim, so we're now trying to plan 2 to 4 weeks out. And so this has been able to help our planners out because now they have more time to plan for work. So the current equipment we have monitored across our whole fleet, all of our main turbine generators have the monitoring on it, which is 14 of them. That includes 11 coal units, 2 combustion turbines, and then 1 steam turbine that feeds off the combustion turbines. All of our main boiler feed pumps, which includes motor-driven boiler feed pumps and turbine-driven boiler feed pumps, induced draft fans, balance of plant, and then at the end of last year, we installed motor current signature analysis on one of the plants across the entirety of the plant. So the way that we kind of chose where we were installing this was by criticality analysis. So the very first things we installed it on were the most critical. So main turbine generators, if you lose one of those, the unit's dead in the water. So that was the first place we installed them. Then the boiler feed pump turbines. They're also, if you lose one of those, either you lose the unit or you're going to lose half of a unit depending on the configuration of it. Then we started focusing on machines that had issues. So things that had issues where we were trying to figure out, why is this thing having issues? So we wanted to put continuous monitoring on it. So we have a combined cycle combustion turbine unit. So it's 2 combustion turbines. They are both, basically a big jet engine turning a generator. The exhaust off of those 2 engines, there's a boiler at the end of it. So the boiler, they create steam from the exhaust. That goes to a steam turbine and powers a steam turbine. So at that plant, it's a 700 megawatt plant, and there are around 30 employees monitoring that plant. So they do not have anybody at the plant that is a predictive maintenance technician. So they have elected to try to implement as much online monitoring as possible so that we can help them out, and Black and Veatch, the MND Center, can help them out finding issues ahead of time. And they're also the plant that did the motor current signature analysis. And now there's 2 reasons for motor current signature analysis. One of the big reasons for MCSA being online is that we have plants where to do MCSA you have to open up live cubicles, because you got to clamp an amp clamp on all 3 of the leads in order to get current data. So we're looking to implement this across the fleet to eliminate the safety issue of somebody having to open up a live cubicle. And then 2, we're now getting data continuously from these motors. So anytime a motor starts, we get the peak amps, we get a torque curve, and we get a starting time. And all that data gets shoved into the MND Center so they can look at the starting time over a period of time, and if they see these motors are taking longer to start up, they can trigger something. We also see a rotor bar. We look for rotor bars, so there's a threshold limit for broken rotor bars, so we should be able to trigger on rotor bars, and several other parameters in the system to try to find issues earlier. So what's the future for us? We've been a lead user of wireless sensors for NI. They developed these about 2 years ago, and last fall we installed the first set of them. So these are sensors that are designed to replace route-based data. So it's not a critical piece of equipment. It's something that you may take data on once a month or once every 3 months. So rather than having a person going around taking data on it once a month or once every 3 months, these sensors collect data typically once a day or more depending on how you configure them. But if they're once a day, it's around a 2-year life cycle, or a 2-year battery change is what we have been told. We've had them now running for 6 months, and we've not seen a huge deterioration in the battery on any of the ones that we have. And these are actually happen to all be outside. So it made it through if anybody's familiar with the cold snap that happened last winter, it got down to about -7, and these were out on a cooling tower, and they were covered with ice and didn't have any issues with data transmission. So, and these go through the same system as the online monitoring or the wired systems, and then also go into the remote monitoring. So our goal for some sort of vibration collection is to have everything monitored in 5 years that we're currently doing a route collection on now. So there's some assumptions that we make with that. The guys doing these rounds for vibration collections, they can find issues that may or may not even be involved with the equipment that they're on. So there's some onus being put on the plants that the operators are going to have to fill in these gaps. The operators are already supposed to be walking these paths twice a day, so it'll be more important that the operators are doing this and being cognizant of what they're looking at and what they're listening to and what they're smelling, because it'll be solely on them to look at this stuff for vibration. There still will be oil routes, but we don't do oil analysis on all of our equipment. It's only on portions of the equipment. And this is some of the monitoring that we're tying into the system this year. For anybody that has transformers, I know Alan talked about them yesterday. For bushing monitoring, we're going the thermal imaging route. So this is a camera that you mount permanently, and you can make it look, you point it at a transformer or whatever else you want to point it at, and you can pick points on the picture, and it'll just stream data from those points. So if you have one picture, you could have 20 or 30 different temperature points that you could have regions, and it'll collect all that data and send it at however rate or whatever rate you want it to send at. Generator flux probe monitoring. Our generators are synchronous machines, so they're running 3,600 RPM, which is why all of our electricity is at 60 hertz. If they don't run at 3,600 RPM, there's serious issues. But one of the issues we have with the generator, and it's on the rotor, is you'll have shorted turns. So the rotors on these generators are wound with copper in them. And if a rotor bar shorts out, then you start getting these deflections in the rotor, the generator rotor, which causes it shows up in vibration. So we're hoping with this type of monitoring that we'll be able to catch these shorted turns sooner, so that we can possibly fix them without having to do a complete rewind of a generator. Because typically that's what happens. It gets to the point where it's so bad that you have to rewind the generator, and rewinding a generator rotor is anywhere from $1 million to $2 million. And then finally, generator shaft voltage current monitoring. So again, it's trying to see what is going on this time with the shaft. So there's brushes on the shaft that keep the voltage and currents from building up in the shaft. And so there's some information that you can get by monitoring that. This goes along with, we're also implementing dissolved gas analysis on the transformers this year. So that's another part of the thermal imaging, or another part of our monitoring package. So lessons learned. Get IT and compliance involved as soon as possible. If you think you're doing one of these projects, get somebody in IT involved, because I've heard a couple of people say it now that IT puts the no in innovation. And it is no kidding. If you say, hey, I got this new fancy thing and I want to put it on our network, the first thing they say is no, we don't want that on our network. So you have to get IT's buy-off on it. And then as well, you got to get corporate compliance, because if either one of them say no, you're dead in the water to begin with. Completing criticality rankings. So if you plan to put this on a bunch of equipment, or even before you start putting on equipment, you really got to know what is your critical equipment, because that's your biggest bang for your buck when you're installing these systems. Because if you can find or stop or prevent a high impact, low probability error or issue, it pays for itself pretty quick. I mean, finding a wiped turbine bearing during a startup, we were able to basically delay the outage a little bit, delay the startup, replace the bearing, and the unit was off and going. So had that not happened, it may have been 2 months down the road that it would have caused an issue. Develop historian structure. If you're going to use an MND Center, developing the models is not easy. So if you have templated structure of your historian, it makes model learning and then model retraining much easier, because you're not having to go in and say for every point, these are the 6 tags that I want it to model against. So by having a template, it knows that on this machine, this point always uses these 6 tags. Creating a naming convention for features. So if you have lots of people from different places looking at the data, you want it to be as consistent as possible with the way you name things. Then finally, creating a standard operating procedure for setting up the equipment. So when you start setting up all this equipment, you don't want one plant to set it up one way and another plant to set it up another way. So for consistency, you need standard operating procedures to set up the equipment. And then finally, lots of training. There can never be too much training. Anytime we go out to the plant, we try to go over something at one of the meetings that we're in to show some new feature, or just to go over a piece of equipment that has an issue, and we try to do it inside the software just so that we can keep people abreast of what's going on, and so that their eyes are staying refreshed to the software. Oh, there's what I thought was going to pop up. So this is our standard for naming convention, our standard naming convention, sorry. So it's just got plant, the unit, anything with Insight CM has this designator, then the machine designator, what component it is, which end of the machine it's on, the type of sensor. If it's an accelerometer, it could be single integrated, which means we're going from acceleration to velocity, and then the feature that's being calculated. So for every piece of equipment that we have, it all follows that same naming convention. So if nothing else, you're looking for a component at a plant, and you know the plant and the unit. Well, if you put plant, unit, and ICM in, it's going to give you every single point in pi that we have on any of that equipment.
John,
Yes?
this slide that we are looking at, this is a component, is that correct? It's a sensor?
Yes, this is to a sensor, yeah. It's a sensor, and more specifically, it's to a feature of that sensor.
Okay, but it's a sensor. It's really not an asset. It's a sensor.
This is the sensor, yes.
Gotcha.
But it's more specific, because the sensor part ends right there at the ACC.
I hear you.
And then after that, it's saying it's a single integrated, so it's going to be in velocity. And then this is crest factor.
Are you storing this record in Maximo?
This record is being stored in pi,
But not in Maximo?
not in Maximo.
I heard that.
So
Yep.
it's like the identification of your tag.
What's that?
You are identifying your tags by doing this.
Yeah, this is the tag. If we look in pi, this would be the tag name in pi. So when you're pulling up this data in pi, like if you had plant and unit and ICM, you would see all of that plant's data. Whoops.
How many total devices
How many total devices for Pi?
Given plan that you've got, if you had to get
How many Pi points?
Pi points,
Oh man, it's a bunch.
100,000,
Uh, for one plant, probably.
okay.
Maybe not quite that many, but it's a lot. I mean, it's anything that's in our DCS for operating, and a coal plant. Let's make it more specific, because a gas plant, there's just not as much equipment there, so there's a lot less data in Pi. But for a coal plant, a coal unit, you're probably looking 25,000 points per unit, because you got anything that's in the DCS is streamed into Pi, as well as all alarm values. So anytime an operator alarm triggers, that's also stored in Pi. So, any other questions?
I see you measuring shaft currents. How you doing that?
So there's a brush rig that's that touches the shaft, and it's they have a current transducer, and it actually goes into a compact Rio, and they measure the voltage and the current off of that lead. But there's a company, it's called Cutsforth, that has the system that does that.
Lots of time for questions.
I guess one question I have is, I guess most of this stuff is cloud-based, is that right?
No, this is all local to our
So it is all
network.
local.
So all the servers, each plant has its own server. So, and the reasoning behind that was, if there was something that occurred that would take and disconnect the plant from the network, all the data that we're collecting is still being stored at the plant. So we wouldn't have access to it downtown or anywhere else, but the plant would still have access to that data. One of our goals and one of our cost justifications of the system was to eliminate the other software and quit having to support that software.
That was it.
Once this system was fully operational, it's in place, right?
It's not completely in place.
Okay, for one given plant, maybe?
We're getting close.
Yes, sir.
So our 5-year goal is to have it completely in place.
Okay. If you were able to extrapolate a guess, what would be the first major benefit observation takeaway that you discovered that you didn't know before? You understand?
Well, we've had one of the issues that we had back in January. I guess it wasn't something we didn't know before, but now we're getting the information a lot sooner, because on a lot of these pieces of equipment, we were only taking data once a month or once every 3 months. So if something happened the day after you took a route-based data, you wouldn't know it for 30 days.
I appreciate that, but can you relate to any specific asset that was high risk, high criticality that, ooh, this is interesting?
Well, we have had pumps where now we see issues with pumps that we didn't know we had based on some valve setup. I had made the comment that we'd had issues with a set of pumps, we had some issues, and we just installed this system on it so that we could get more data on those sets of pumps. And we finally figured out that a check valve was replaced during commissioning, and it was the wrong size check valve, but the body and everything looked the exact same.
Human factors.
Uh-huh.
Any additional questions? Okay. Thank you very much.
Thank you.